We have to finish off a little bit about Fermat, and then I don't have slides for the talk about Schmidt and Leibniz. So let's see how
So you're going to freestyle?
Mostly freestyle. Remember we saw him, he was known as the Prince of Amateurs because he was really an attorney. In fact, an important attorney, right? He was eventually appointed to sort of a major position in the courts in southern France. But he was also a mathematician. He's famous, I guess, today, mostly for Fermat's last theorem. People in math always abbreviate this FLT. But in physics, that's faster than light travel. So every time I see FLT, I kind of have a disconnect. Wait, what?
Well, for the longest time, we thought that both were impossible.
Well, now we know that his is impossible, or rather that his is correct, but his statement is that something's impossible. So x to the n plus y to the n equals z to the n has no integer solutions except for trivial ones, where the numbers are zeros and ones. That was what he suggested. Now, I want to point out that if it doesn't have integer solutions, it also doesn't have rational solutions.
Why when n is greater than 2?
When n is greater than 2, that's right. I'm sorry, I should have put that in. So suppose you had a rational solution to, that is, you had markers.
Oh, so that means that you can multiply it by whatever that,
Yeah, right.
if you see something on the bottom.
If you had a over b to the n plus c over d to the n equals, I guess it's e and f for the other side to the n, then you can find a common denominator for all this junk. It's b to the n, d to the n, f to the n. Right? Add them all up, and now, or not add them all up, multiply by that, and you've cleared the fractions. Right? So then you'd have an integer solution. So that would be the go against what Fermat's last theorem. So I'm using the modern notation for this. Of course, Fermat wouldn't have, but I'm not clear. Does everybody know the backwards E?
Never seen it.
Yes, you have. You, I know, but not everybody. That means exists. So this is saying there exists a triple of letters, triple of variables, x, y, and z there in cap Z. Made with this funky font means the integers. So they're whole numbers or possibly negatives of whole numbers. But for this problem, add plus and minus really isn't an issue either. If you have rational points, how to put this? If n is an even number, then it really doesn't matter, because what's the difference between a negative number to an even power and just a positive number to an even power? They give you the same value. If n is odd, then you do have, you have cube roots of negatives. You have a different value for the odd powers of a negative number than from the odd powers of the corresponding positive number. I'm sorry. You know what I'm talking about, right? Okay, so no rational points on that curve, and that actually is an area of active study. Hey, how you feeling? Can you speak at all? Yeah. Stay away from her, by the way, everybody. Could be contagious. So yeah, finding rational points on curves is an important area of research today. In fact, rational points on curves often mean the solutions of other types of problems. So this is a bit of a strange idea if you think about it. That curve x to the n plus y to the n equals z to the n has no points on it where both coordinates, both x and y. Oh crap. Sorry. There's one more thing I had to say before I jump to saying that. If I have an equation like this with rational numbers, can I make an adjustment so that this thing on the right is 1?
But we're
Could I turn it into something to the n plus something to the n equals 1? If I had a solution like this with rational numbers in it, well, yeah, just multiply by f over e to the n. Just clear that, turn that into 1, and you'd have to do something on the other side too. But distributive law works, and so you'd have a rational solution of, that is, this also implies there exists x and y, but now I'm going to put them in the rational numbers, such that x squared plus y squared is 1. These x and y are different from those x and y. Because those guys were integers and these are just rational. So what does that say? I can look at a single curve. X squared plus y squared equals 1. What's that look like? I said squared, didn't I? Yeah. No, I confused you because those guys are n's and these guys are supposed to be n's. You know what happens though when you write x to the something plus y to the something equals 1? Your brain automatically jumps to thinking about the unit circle. Right? So that's what I did here. When n is 2, you get the unit circle. What do you get if n is 3?
Not a unit sphere, but a unit z.
Well, because it's, yeah, right, it's two-dimensional, right? So it's not that.
Unit cylinder?
Well, again, that would be a three-dimensional object, right? So I'm really only thinking in 2D. So I got x cubed plus y cubed equals 1. One thing is, in the first quadrant, it kind of looks like the circle, except if you took the circle and put a square around it, and then kind of blew it up a little bit so that it would inflate into this area between the squares, that's what's really happened here. This is not circular, it's a little bit more up into the corners than the circle is. It's a little pushed up towards the diagonal. And then it actually goes off like that in there. So that's what x cubed plus y cubed equals 1 looks like. Now that, yeah, you can solve for y, right? And so you can plot that on your graphic calculator as well. Not a problem. And all the odd powers look like this, and all the even powers look like circles, except squared off circles. So if you get to x to the 4th plus y to the 4th equals 1, going to challenge my artistic ability here a little bit. It looks like a square with the corners rounded off. Is that kind of the idea? And people call this the squircle.
Squircle?
And actually, I should make a plug for the MAA meeting that's coming up. We're right around the Thanksgiving weekend. There's a meeting of the Northeastern section of the Math Association of America. A bunch of people from Southern are going to be going because it's just down at Sacred Heart University, so 40 minutes away. 50, depends on traffic. But there's, and by the way, I'm going to be the chair of the Northeastern section after this meeting, so I'm trying to promote the organization. It's really interesting if you're a math person. There's like a lot of activities for students there. In fact, we put out a note trying to ask people if you're interested in making a presentation. We can make a presentation at the MAA meeting. And frankly, it doesn't have to be, that big of a deal. Like if you have an idea from this class that you're like, oh, I could put 5 or 6 slides together and talk about that, you can do that. And so it's very low threshold, but awesome when you're resume, right? To be able to say you did a presentation at a math association. Anyway, presentations for students. There's a big student math contest where you work in teams to solve impossible problems. Not quite as impossible as Putnam problems, for those of you who have been following that, but still hard. And it's a lot of fun. There's a cool banquet. Usually there are very interesting speakers who give accessible talks, not necessarily talks that go off into huge technical detail. There's 2 major associations for math: the American Math Society and the MAA. MAA is more focused on teaching and pedagogy and promotion of math. AMS is where the hardcore, talks that nobody can understand. Usually, I shouldn't diss the AMS. They're good people. But I'm with the other guys.
Why do the edges of the squircle not show up?
They don't show up. You try to plot a squircle? Oh well, it's just that they're not on the pixels. Right? You've got to change your zoom a little bit and maybe you'll put it in there. Yeah, so look, this is basically like a circle, right? And it's a little bit bowed out into the corners. There's actually another kind of funny point about the squircle. There's a Danish architect named Piet Hein who really loved this curve. He called it the super ellipse. And he created this. He didn't know that he was not the first person to think about it. But he created it because of a practical problem. They had to make a traffic circle in a city square in Copenhagen. And they wanted to get more area in the middle to use as a park. And a circle would have been just fine, but if he made it a squircle, he got more space in the middle. So there's actually a squircle-shaped roadway in Copenhagen. If you want to go there, you can. It's part of like math tourism. Go through Europe and find one of these spots. I was starting to talk about the MAA because one of the previous chairs of MAA studies this stuff, the squircle. Remember how in the ordinary circle you have cosine and sine give you the coordinates of a point? Well, we do the same thing on here. I just say, okay, instead of radians, we'll have arc length around the circle. And you tell me a certain arc length, I'll tell you the squine and the cosine of that. Yes, that's his job. So, yeah.
You couldn't use the polar coordinate thing where x is r sine theta, and then you would still get the same thing.
You can make a conversion to polar coordinates, and you get r as a function of theta, and get it to trace out the squircle. You can do that too. But his thing is actually to make arc length around this thing, the measurement, which is not quite the same as an angle. An angle is arc length around this guy, and there's slightly off. There's the whole topic of doing trigonometry on a squircle is called squigonometry, which I just think it's one of the most brilliant names that anybody ever came up with. Anyway, you see the pattern goes on from here. We'll have squircles that are even more squircly, right? They push out into the corners more if you go to the 6th power or the 8th power, 10th power. All of the odd powers have roughly this shape, but they get closer into the point 1, 1. And anyway, what's weird about these curves is this guy and the n equals 2 case has rational points all over it. Every time you have a Pythagorean triple, you can divide by the hypotenuse and get a rational point on this curve. Right? So that it's covered in points whose coordinates are both rational numbers. This guy has 2. There's one here and there's one here, and that's it. This guy has 4, but they're not very much more interesting. Okay. And all the even powers have 4, and all the odd powers have 2. That's what Fermat's theorem says, really, in terms of rational points on curves. Yeah, and it's true. Now, I don't know how to think about this because, there are certainly x coordinates in here that are rational. But if I go up to the curve, what this is telling me is that the y coordinate won't be. So anytime you have a rational number as the x value, the y value is going to be irrational, and vice versa. Bizarre, right? I mean, it's a strange coincidence, but that's really what Fermat was noticing there. Okay, having said that much about Fermat, let's push about that particular thing, because this guy did not just do that. That was one little remark in his notebooks found after his death, or actually a copy of Diophantus scribbled in. Probability. The entire subject really was founded by Fermat. And many people know about Pascal. Have you heard of the Pascal triangle? Okay, so Pascal's triangle, the reason he was interested in that is those numbers that fit in the triangle. 1, 1, 1, 1, 2, 1, 1, 3. If you hadn't heard it called the Pascal triangle before, that's the triangle I'm talking about. And you could keep extending that forever. The reason Pascal was interested in this is it counts how many choices you have in certain things. And he was interested in gambling. So in gambling, I think probably the most famous one would be in row 52, index 5 in there, way down the table, right? In modern notation, it'd be written like this: 52 over 5 in parentheses with no fraction marks, so just 52 over 5. That's how many ways you can choose 5 things out of a set of 52. Why is that important? Over, right? So Pascal wrote to Fermat with a question they called the unfinished game, which is kind of a weird thing that has to do with the period at the time. The people who gambled were all these noblemen, right? Nobility had time on their hands, they did stuff like this. But strictly speaking, it was illegal. So you'd have all these nobles around in somebody's house normally gambling, and then the cops would show up. And they would just hide everything, and that meant they couldn't finish the game, right? But suppose, in some game of chance, me and Vasana are playing, and I'm like 30 points up on her. Does that mean I won when it got cut off by the cops showing up? We've got this pile of money that both of us put in equally, right? And we're gambling on that stuff. How about that? Should I just pull it, take it all? Should we just each take our stake back and say the game never happened?
Or you can, what was it, so like, it's up to 30 and it's an E to 50.
Well, yeah, maybe the game was only to 40, and then in which case,
75 to 75. Then,
should we divvy it up like that? Yeah. So what Pascal said is we should figure out what's the reasonable chance that I would have won from there, and the chance that she would have won from there, and then we would divvy the pot up based on those probabilities. Essentially, we didn't call it probabilities yet. That was the idea. So he wrote to Pascal about this question, about how to divvy up the money in an unfinished game of chance. Because you have to figure out, what's the probability of future stuff happening. And Fermat liked the problem, and he responded to Pascal. They had a long correspondence going back and forth, and he kept trying to get Pascal interested in something else, but Pascal didn't want to hear it. He was really interested in gambling stuff. The other thing that Fermat wanted to get him interested in is what he was working on. This is the translated from French, actually translated from Latin title, A Method for Determining Maxima and Minima and Tangents to Curved Lines. We call them curved lines, we would have said just curves. This was looking at an ancient Greek text again, a thing called Plain Loci by, I'm not sure how to say that, Loci. I was just watching Thor last night, and Loki is a different guy.
also, you can't forget about low key. You want to stay low key about something.
Right. There's a famous novel that has a guy whose name is Loki, but later it turns out he's Loki.
Clever.
Yeah, I thought it was clever. I didn't catch it until I started going, wait, all these people have something to do with Norse gods, and then I find out. Anyway, what does this sound like to you? Methods for determining maxima and minima and tangents to curves?
Sounds like calculus.
It sure as hell does. So really, a case could be made for Fermat as the guy who had come up with calculus way before Newton and Leibniz, who we'll talk about later. And that's what he was trying to get Pascal interested in. Pascal wouldn't really go there. He also really gets credit for joining algebra and geometry. I mentioned when we talked about Descartes that his idea of the Cartesian plane made that marriage possible. But Fermat's the one who really conducted the service. You know what I mean? He really made them one thing. We're at the end of Fermat now. Yeah, I was lost. Okay. So,
Quick question about Pascal.
Yeah.
Is that the same Pascal from Pascal's wager?
yes. He was also a philosopher. Does everybody know Pascal's wager? That's not necessarily a common knowledge sort of thing. He was curious about the existence of God, and he basically said, let's do this as a bet. Right? He was very interested in bets, I guess. If God exists, and I believe in Him, and I go to church every day, and so then I'm going to get this ultimate boon at the end of my life, right? I go to heaven and live forever with angels and get to play harps, which are cool. If God does not exist and I do all that stuff, what's happened? I've wasted all the Sundays in my years. And I've used 70 years worth of Sundays. And I was acting like a good guy all the time. It's, I guess maybe there's some pull to wanting to be evil, but he was saying, not a big loss really. On the other hand, if God, if I screw around and do whatever I want, maybe I don't want to go into examples. Let's just say be a bad person, whatever bad person means to you. Don't go to church. Yes, partying and smoking and drinking all the time. They probably didn't smoke yet because I don't think they got that until Sir Walter Raleigh came back with the tobacco from the Americas.
Fornication.
Fornication, that's a good word. And I can say it in public, so cool. Yeah. Yeah, but you know what I'm trying to say. And just being a libertine, I think, is what they would have said at that time. If God exists and I do all that stuff, it's ultimate punishment, right? So the spending the rest of eternity in agonizing pain. And if he doesn't, I got 70 years of getting to do this stuff, which you probably could have gone without. So the idea is to look at it as a wager and a probable, what is it called?
Cause.
No, I'm trying to think of the word.
Expected value.
Thank you. Probability is not my strength. Your expectation is what you expect to win or gain or lose overall in a wager. And the expected win, if you believe in God, is huge compared to a small loss. And the expected loss is huge if you don't believe in. If you behave as if you don't believe in God and he does, you're in big trouble, right? Whereas the expected plus side is 70 years worth of drinking and partying and dancing and debauchery. That's a great term for it. Again, not a huge win compared to the potential loss. So what should you do? His idea from the wager is pretend like you believe in God even if you don't think it's there because of the payoffs.
I feel like there's a lot more. I feel like there's a big argument that there is a decent amount to lose.
A decent amount to lose in terms of not going to be debauched if you well, there's one saint, I forget his name now, who pulled that stunt. He basically lived an entire life of debauchery, and then on his deathbed, he recanted very sincerely, and that was good enough.
I was going to say, it depends on what time and what God you believe in. Because a lot of them, you can just go, I'm sorry for everything I did. And, if you're sincere, then it's okay.
Well, I think he also had the Pope actually come to his deathbed, so there was some element there where he had like the guy, right?
Yeah, that's nice.
Yeah, but I don't think that worked for most people.
But that's literally what it's not to mess up. What you gotta do is just be like, yeah, I messed up.
My bad.
It's all good, right?
But then you also have to try to not be that in the future.
No, it says nothing about that. You
Oh,
can
yeah.
do something over and over again as
You can
long
go
as you're sincere, quote unquote. He welcomes you back with open arms.
Oh, crap, sorry.
All right, let's not get
I
into
get
this
up.
conversation.
Who is this man?
I don't know,
We
but
have two choices. Come on, who am I talking about today?
Leibniz.
I don't know, I really want some fix for some reason.
That's Newton.
I
That's the
knew
most
it.
famous portrait of Newton. And wait, actually the other guy. Linus. Now look at the pair of them side by side.
Are they not the same person?
They got
Who
the
would you
same
like to hang out
hairdresser.
with? They both wore wigs. Certainly for the portraits. But I feel like Newton looks like a jerk to me. He's like looking down his nose at you. He's kind of got a superior thing. And Leibniz is smiling and,
I think his eyes is gentle.
he has, so Newton had a hard life, I gotta say. His dad died. His dad was also named Isaac Newton. Interestingly, was completely uneducated, though he was fairly wealthy. He was a landowner. He had some animals, herds. So Newton didn't want for much as a child, but he had no father until his mother remarried, and apparently there was no love lost between him and his stepdad. I like this one thing I read about him. Is at the age of 19, he decided to make a list of all of his sins, the things that he had done wrong in the course of his youth. And one of them was threatening to burn down my father and mother Smith's house around their heads. Yeah, that's a rebellious teenager for you right there. Right? He apparently threatened arson and killing them by arson. So that was but yeah. So I find it interesting to sort of just think about how often it is that these famous people who do amazing things have terrible childhoods. You know, there's like one of the classic examples is Churchill. You guys know who Winston Churchill is? If you see a newborn baby boy, they all look like Winston Churchill. Fat jowls, bald. You know, he's famous leader. He really got the Allies through World War II. But his childhood was miserable. He really, you know, his writings are almost pitiful when you look at the attention he seeks from his mother, who doesn't give a shit about it. To have a mother who doesn't care about your child is a little bit of a weird phenomenon. Anyway, that's me with Churchill. Newton's upbringing was similar. His wife remarried, and his mother remarried, and she was into the new husband, not the previous dead one. And she just didn't. I don't think she cared for it very much, and certainly the father, the stepfather. They say his life fit into the sort of three sections, and I'll mention the three. One is what in the History of Math Archive they call his childhood, which lasts for 24 years. So I'm not sure. In that era, childhood usually was over by 15 years old. Grown up by then. But at the age of 24, he accepted a chair at Cambridge University, and the chair was named after somebody named Lucas. I think an industrialist who made a fortune in mills, if I recall correctly. But it's now called the Lucasian chair. And there's still people who hold the Lucasian chair in mathematics at Cambridge. There's one person who did that. I'm curious if anybody knows the Lucasian chair in math.
Is it Stephen Hawking?
It's Stephen Hawking. The guy in the wheelchair who's like kind of terrible disease that he talks via computer. He's been on The Simpsons. Anyway, so that's a famous lineage. Newton was the first Lucasian chair, and that chair has been occupied ever since his time.
So that would be a horrible joke. Like the chair, Steve Hawkins in the chair.
Oh, what?
Like Steve
No,
Hawkins.
it's just
Yeah, it sounds like
chair.
an achievement.
It literally meant a chair at the dinner table. Okay, so there's a banquet table, and people who had. It's again a little bit like Hogwarts. You know the scenes where the kids are all sitting in the tables at rows, and then there's a head table with all the important people, the schoolmasters. Yeah, those are the chairs. The chairs for the fellows of Cambridge.
Did they all have a name?
Yeah, I believe they're all endowed chairs. So yes.
Did anybody have it between Newton and Stephen?
Say.
Did anybody have it between Newton and Hawking?
Oh yeah. It's been so. This was he was the chair. He had the Lucasian chair in like 1690, and it's been occupied ever since then. Lots and lots of famous people actually. I wish I was prepared to tell you, but yeah, lots of sort of whoever the most prominent mathematician in England at any given time would have been in that chair. That's the point of it. Oh, okay. If somebody were from Oxford, they might. Not want to go to Cambridge. It's sort of it's like southern and central. You know?
There's also like
Right.
Yale and Harvard.
Yale and Harvard. Maybe it's a little more like Yale and Harvard. So anyway, while he held the Lucasian chair, that's where he did the math, and he figured out his method of Fluxions, working out from calculus, along with lots of other things. The biggest problem with Newton was a character flaw that he wanted to get the approbation. He wanted to be regarded highly by other mathematicians. So he solved all kinds of challenge problems. Like, for instance, there's a question called the brachistochrone, which is you have a wire that goes from a high point to a low point, and you have a bead that slides along it. And the idea is the bead can go perfectly without friction. what shape should you put that wire in so that the high point and the low point are connected, so that the bead will slide from A to B in minimum time?
Maybe a straight line.
Straight line doesn't quite do it. What you really want to have happen is the bead should accelerate up to a high speed a little early first, and then make it to B. So you want some kind of a downward curve, or a concave up curve.
A squircle curve.
No, Squircle doesn't do it. If you go to MoMath with the Math Club, they have a contest, an exhibit about this, where you have a flexible track, and you have little cars that run on it, and you try to set them up to fit the Berkistikone curve. And the curve, whoever, if you release the two cars simultaneously, whoever's closest to the Berkistikone curve is going to win, because their car's going to reach the thing first. Except that little children come in and try to make the crack go like through all kinds of craziness, and they're constantly breaking that exhibit. Anyway, so you should go to Math Club to MoMath, right? No, not happening. Maybe in the spring. Well, I thought you were all on board.
Not enough interest.
Well, guys, come on, we gotta go to Math Club. Huh? Okay. So he'd solve problems like that. And in fact, the answer for that one, I believe, is a cycloid. But it's kind of not the important thing. The point was that Newton had this calculus method in his back pocket, so he could solve problems like that. That's a minimization problem. Minimize the time. That's actually a calculus of variations problem, they call it. But still, it's that sort of method. But he didn't want to tell anybody about his secret weapon. He had this method of fluxions that he was using to make himself even more and more famous. Why tell anybody else about it? Then they would all be able to solve the problems that he was solving. So he would literally solve a problem via calculus, and then sit down and laboriously write up a proof in classical geometry, figuring out things via the loci of curves, the way Fermat talked about it.
That's some dedication.
Yeah.
Yeah, well, he just didn't want to give up his secret weapon, so that was the big problem. So Leibniz comes along and he said, "Hey, everybody, I've got this method. I'm calling it derivatives." and Newton is like, "No, I already did that. Well, why didn't you publish anything?" So that was the big debate. Well, Leibniz figured this stuff out and went, "Wow, I got to tell everybody." Newton figured this stuff out and went, "Nice, keep this here and use it." I gotta see if I can find the XKCD cartoon for y'all.
It sounds a lot like me.
Wait, I think I know what you're talking about. It's
And
like,
the
oh, I invented
famous for
calculus.
inventing it.
Yeah.
Yeah,
That one?
yeah.
So wait, so which one was the hard ass? Leibniz or Newton?
Hard ass?
Yeah.
I would say Newton seems from the picture, it looks like a bit more of a hard edge guy. Have people seen this one?
Yeah.
Yeah.
Newton in 1666 says, "I've invented calculus." How much later is this? 12 years later, Leibniz is saying, "I've invented calculus." Do you get the thing of putting on the glasses and saying, sounds a little, and then saying some punk? What is this TV show that is? CSI. And I don't know why the mouse over text says, "Yeah."
Because that's
That's
also
what it goes into.
That's what happens. But yeah, I do like putting on the sunglasses way before sunglasses had ever been invented, no doubt. Plus, this guy, it doesn't look like Newton with his wig. It looks like some kind of a bad mullet. You know? I'm like, does the guy from CSI Miami have a mullet? This is a little bit old at this point, right? CSI Miami has probably been off the air for 10 years. So the big period of time left between them. We should talk about the notations. And some of the misconceptions. One of the big evidences that Leibniz brought to this controversy was that Newton didn't quite understand partial derivatives. And Leibniz's approach did deal with partial derivatives properly.
So this is why we find both of them, because they were both partially right.
Right?
Well, no, the partial derivative has to do with getting parts of the information about the change in the output with respect to the input. So if you have a function, f, and x is its input, then we write f of x as the output. This is how Leibniz thought about it. So this is the Newton just said x is getting transformed into y, and that leaving the function unnamed. That is, he would have things like, well, actually, I misspoke a little bit. What Newton would really have thought about was time getting transformed into y. Because he was really interested in questions about motion. So Leibniz was thinking more generally. You have functions of, whatever, turning something into an output. Newton was just thinking everything is time, and t gets transformed into y. So for instance, you might have y equals t squared. Then Newton would talk about the first function of y, and it's what you know, 2t. And that notation morphed into what we use today with prime. And if he wanted the second function of y, it would be that thing, with two dots over it. And then he would get 2 in this case. Leibniz had this much more complicated notation. So he would have, there's two ways to think about it in terms of functions, though. But let me work just with variables first. When we do this stuff, when we turn t squared into 2t, what we're really doing, because of the Leibniz version, is figuring out the slope of a tangent line. So what Leibniz really did is say, okay, once you've got the tangent line, however you get that, what I'm interested in is motion along that tangent line. And if I move over a certain amount, I'm going to move up a certain amount on that tangent line. In other words, he's thinking about new variables for the tangent line. What are you going to call them? Well, they were related to x and y, but they weren't x and y. He could have put primes on them the way Newton did, or dots on them the way Newton did, but he wasn't thinking about them. Everything's a function of time. He was thinking in a more general case. Things are functions of whatever. So he just decided to adopt the delta x notation. That was common, and even back then, delta x would refer to a change. But this was something different, so we called it dx. And this is dy. Well, okay. So once you're in the tangent plane and you've got coordinates that are called dx and dy, those were single entities, right? Even though it looks like two letters, he was thinking dx is one thing, dy is the other thing. What's the slope? It's dy over dx. So your m here is dy over dx. That's the Leibniz notation for taking a derivative. Now people adopted that later to say, this is like taking the derivative with respect to x of y. Right? But that's not how he was thinking of it. That's a modern, or at least an 1800s, reinterpretation of what he was doing. This is how he thought of it. We've got a tangent line, and we've got variables in the tangent line. He also, by the way, would have thought about tangent planes. That is, what if you have a surface? Right? You have a big wiggly surface that's sitting out in space. Z is related to x and y, for instance. Well, now this line turns into a plane. It's like a Post-it note stuck on the surface. So I'm going to try to draw you a picture of a wiggly surface by filling in a bunch of level curves. We'll reverse it up. Yeah, that one changes direction. You get the general impression of a wiggly surface here. If we're at a particular point on that surface, z is a function of x and y, you can draw a flat plane there that is tangent to the level curves. And if I'm careful enough, I'll draw in at least a little bit so it looks like a window pane there. Now in that plane, you again have changes in x and changes in y, but you also have changes in z that happen. Actually, in this case, we go down a little bit. So you have dx and dy thinking of that as a function machine, the way I was talking about here, what we're seeing is a function that has x as an input and y as an input, and then go into f, and out comes, well, f of x and y, but that's it. If you take derivatives of this, you get part of the information about the change in z from x, and you get part of the information about the change in z from y. And you need to put those two together to get the total derivative. That's why he talks about the partial derivatives. And you've seen the modern notation for that would be the function's x partial plus the function's y partial. Well,
Never seen them added together though.
sorry?
Never seen them added.
You never seen the partials added together? That's called the, here, let me show you the thing. This is information about a slope in the x direction. That's information about a slope in the y direction. If you take the partial with respect to x and multiply it by dx, and the partial with respect to y, and multiply it by dy, you get the total partial, the total derivative. You see? That's called a linear approximation to the function. Those have to be evaluated at the point, right? So, but that's how you get the equation of what's moving in that tangent plane. So the Leibniz notation, well, people really don't like the Leibniz notation at first in calculus. Did you guys have that feeling in Calc 1? Why are we learning two notations for the same thing? And I just like the primes. I think almost everybody goes, I like the primes. Let's do the primes. That's Newton's version of things. It's much easier. So let me show you one place out of many where the Leibniz notation is actually more useful. Let's look at the chain rule. Remember the chain rule from Calc 1?
Never
If you
seen
look at the Newton version of it, it looks something like this. F of g of the prime is equal to, well, what do you got to do? You take the prime of f and you evaluate that at g of t. And then you have to fix that up with g prime of t. What Leibniz notation would have said for this scenario, where you have two things to be positive, is what you've got is t getting turned into x, and then x getting turned into y. So this is actually the x dt times dy dx. Shit, no, it's not good. Yeah, no, I did it right. So he was thinking, we have time as the input, gets turned into x, and that gets turned into y. Functions. The line from t to x, dx dt. The line from x to y, y dx. Cool. The dx's seems like it can cancel, and you find the derivative of y with respect to time. Do you see the beauty of that? You can treat that Leibniz notation differential stuff as if you had fractions and just cancel them. So the chain rule is like so much easier than Leibniz notation. And there's no question about the f prime of g thing, because, well, where are you going to evaluate dx dt? That's telling me how x changes with respect to time. You have to evaluate that at a particular time. Where are you going to evaluate this? I don't see any time in there. Well, you have to evaluate it at the x that corresponds to that t. So where to evaluate is almost automatic in those things. This doesn't even mention t. All right, so I guess I'll probably stop like that. I'm probably never going to convince everybody that Leibniz notation is better. I think Leibniz is also the one who gets the credit for the integral notation, the integral of something. X squared dx. That wouldn't have, yeah, it certainly is his notation. I don't know if Newton even considered the integral question. He must have reverse of differentiating, right? So, but I don't know what his notation for that was.
Leibniz is better.
I like the actually writing whatever, but more we can do it.
Well, the prime, you know, what's really there is the prime is a lot faster. You put a prime on it, you're done, right? You don't have to.
I think that in the
But you know what, I gotta say one last thing before everybody runs. When there's lots of variables around, you know, when you have X, Y, and Z all feeding into a function to give you a cube, what's prime mean? You mean the X derivative or the Z derivative or the Y derivative? There's too many choices there. Leibniz notation at least has this advantage. It makes it clear what you're thinking about changing when you pick a derivative. To,
I like to like switch back and forth too much. I would have.
oh, by the way, I made some progress on my grading backlog. So I got some new grades on Banner, and I'm about halfway through the biographies now. So I should get those back to you hopefully Wednesday.